Hey guys, and welcome to your video for Chapter 4. In Chapter 3 we talked about ways to graph or display. Those could be bar charts and pie charts versus contingency tables and data tables or frequency tables, qualitative data. Now we're going to look at how we can graph quantitative variables and the data from quantitative variables. So the first slide here is getting at why the displays might be different, at least when it comes to the tables. So last chapter we discussed the primary methods of showing you categorical data included frequency tables and contingency tables. However, quantitative data is generally arranged in a less organized table as you're seeing below. Why might we arrange categorical data so neatly in a frequency table or contingency table, but not with quantitative data? Well, if I had a graph of you guys's let's make something real quick. Not a graph, a table of you guys' eye color, and we had brown, blue, hazel, whatever. The data falls into neat categories that can be grouped by, in this case, brown, blue, and hazel. So you've got counts here. Maybe in a class of 30, we had 15 brown-eyed students. We had 5 who were blue, and then 10 who had hazel eyes. With quantitative information, like you can see in this large table to the left, the delivery time in minutes here, you've got quantitative data is frequently continuous. Your height, you might say, is 6 foot, but it's probably more like 6 foot and a quarter of an inch or something very different from the next person who could be maybe close to 6 foot but not quite. So you've got, it's just harder to lump quantitative data together. That's the end of the story in that first slide. All right, so just as pie charts, bar graphs, and segmented bar graphs tend to be great for displaying categorical data, we have a few special graphs that we'll be working with very frequently when using quantitative data. First is the histogram, and you've heard me mention this just a little bit in class. So let's talk a bit about what each of the histograms below is doing. Well, first thing you should notice is that it looks a lot like a bar graph. You've got, instead of bars from the bar graph, we call these guys right here bins. Because what we've done, if you look back at the last slide and you consider the delivery time in minutes, if I had made a histogram of this data for the delivery time in minutes, maybe this is of one UPS driver, and the time it takes him to get to his first stop from the UPS hub, the plant where he picks up his parcels for the day to send out. We call these bins because we've thrown all the quantitative data into one grouping. So these groupings for age in years represented at a subway terminal at some city. We've grouped everyone who are between 1 and 5 years old together. Same with 6 and 10, same with 11 and 15, same with 16 and 20. So it's just like laundry bins. You just throw everything, some people throw, before they wash their clothes, everything that's, maybe their reds or their darks together in one laundry bin, then they wash that load. And then they throw all their whites together in the same bin, and then they wash that load. So same thing here. So instead of bars, we call these bins. Just like with the bar graphs, you've got the frequency, also known as, and let me add this in, also known as counts on the vertical axis. So how often do you see data falling into that bin? That's what the vertical axis is answering for you. So you've got for ages 1 to 5, it looks like 4, maybe 5 kids were at the subway terminal within that age. You had 30 kids ages 6 to 10 at the subway terminal. That's kind of crazy. You had like 28, 27 teenagers, 11 to 15 at the subway terminal, et cetera, et cetera. Okay, so very similar to the bar graph, but you're lumping the quantitative information together because it can be so messy, and you're choosing bins here. Notice from the first blue histogram to the second gold histogram that the bin sizes can vary, and they can vary quite a bit. The bin sizes should really vary in such a way that, in general, you want to have 6 to 8 bins per histogram. Now, that can change. As you see it with this gold histogram on the right, you've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bins. But that's okay because you have a ton of data that's represented. You've got the highest bin at between 100 and 110 has 28 candidates represented, and a lot of these other bins are relatively tall. So we've just broken the bins down to be maybe a little bit thinner than they could have been, but you get maybe a truer representation of the data because you have more bins than you do in the blue histogram for age representation of the subway terminal. All right, so bins we use for quantitative variables on the horizontal axis, and counts frequency we're still using on the vertical axis. Let's see, anything else on that? Let me look at my notes real quick. Oh yeah, as you see, there are no spaces between these bins because in this case, unlike with bar charts and bar graphs, the ordering of the bins is significant. It is meaningful that the bin for ages 1 to 5 comes to the left of and right before the bin for ages 6 to 10, which is before 11 to 15, etc., etc. Same with the cost of computer services rendered at a tech store. The order of the bins is important, hence we do not put gaps between them. All right, so there's your histogram. A relative frequency histogram is to a histogram as a relative frequency table is to a frequency table. So basically, rather than putting on the vertical axis the counts, or the frequency as we call them, how many data values fall into those bins, you're putting the percent of all the data, or the percent of the sample that falls into that particular bin. So here we've got a histogram of the height in inches of students in an AP statistics course. And on the vertical axis, it does an awesome job of telling us that that's not the frequency, that's a relative frequency. So these are percentages of the data values falling into each of these bins. You've got, let's see how many bins we've got set up. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So more than the 6 to 8, but we're close. The key is basically to make sure that you can cut it up. You can probably, if you look at this gold histogram right here, you can carry this out logically. If you cut the bins that it already has in half, and then cut those bins in half again, you start to break it up that there are so many bins, your eye can't process what's going on. So far we've seen good examples of histograms. This is also a good example of a histogram. Don't focus too much on the exact number of the bins in the histogram. Think instead of just making sure that you're not cutting it up so much that it's confusing on the eye. We're trying to set up graphs that are easy to understand, they make sense, they don't violate the area principle, which we'll talk about here briefly in just a bit, and look good, and just look good. Okay, so we've got heights represented here. Let's see what this question is below. It says, before moving forward, how do you think data values that fall on the border of our bins are treated for histograms and relative frequency histograms? Why doesn't this problem exist for bar graphs? Well, what they're referring to in that first question, the bottom of the slide, or what I'm referring to, I guess, is what do you do in the case that you have someone who is, the data from them would be 65.5 inches tall? Because as you notice, when you don't have gaps between the bins, suddenly you've got what could be a problem of someone who is 65.5 inches tall falling into either this bin or to this bin. Well, the bottom line is this. Because like we just said last slide, that the bin size can be arbitrary. You saw different widths for these bins visually on top of different number widths for these bins here as well. 1 to 5 is a range of 5, 6 to 10 range of 5, versus 40 to 50 range of 10, 50 to 60 range of 10. So the bin sizes are already arbitrary. That's okay. Same thing here with where you put data that hits the the division between two bins. As long as you're being consistent and you say something like, well, okay, for each data value that hits the bin division, I'm going to put it in the higher bin. So in this case, if we had someone who is 65.5 inches and we put it right over here, that's fine, because we just want to make sure that even though there are some arbitrary elements to creating this histogram, consistency is what allows us to interpret it accurately. So there too, if you had someone who was 71.5 inches, he would fall into this bin, and that's okay. We are going to play with, or I'm going to show you, you don't have to have your calculator on hand for this. At the end of these notes, I'm going to show you how to make a histogram on the TI-84, and the TI-84 takes care of this potential problem with where does the data value go when it hits the division line for you, and you really won't ever have to think about it. But I know that from past years, students had asked about that, and it's not really a problem. It really doesn't matter that much. It'll normally be taken care of for us with the TI-84. Okay, so unlike, well, it is like the histogram. It's just sort of flipped around. You've got a stem and leaf plot. You've got two here, which also show you the distribution of quantitative data for whatever the variable is. In this case, on the left, we got kind of a sad variable. We've got infant mortality rates in Western Africa for countries in Western Africa. And so, I mean, it's just like the histogram, but now on the vertical axis, you've got your quantitative variable, and on the horizontal axis, you have your leaves. This is a couple of things. It's really your frequency in addition to the actual data values. That's the advantage of a stem and leaf plot over a histogram, like we saw right back here. The histograms, as you might have observed, I don't know what people's, looking back at this height in inches of students in an AP Stats course, I don't know the exact height of people who are in this bin. I know that it's in the range of 63.5 to 65.5 inches. Well, the stem and leaf plot gets around that problem because it's showing us on the horizontal axis that for each of these bins, the width, let's make it apparent like this. The width right here does show us relative to the width of all other bins, relative to this guy and to this guy. The width does tell us how often data values are falling into that bin, but also it gives us the exact data values. I know, given a key at the bottom of this stem and leaf plot, that a 9 cut by the trunk 2 represents 9.2% infant mortality rate. So for instance, we have kept the individual data values. This guy right here, for whatever country that is, there's an 8.4% infant mortality rate in that particular country. On the high end, you've got a 15.1% infant mortality rate for some country in West Africa. So that's the benefit of the stem and leaf plot. You keep individual data values. The problem is, as you might be able to guess, it's harder to create. It takes more time. And stem and leaf plots, you might see them maybe a tenth of the time that you would see a histogram in this class. And that's especially true in second semester. Histograms are the go-to way of representing quantitative information, and bar charts are the go-to way for representing qualitative information. All right, you've got another stem and leaf plot in yellow to the right. I don't like it as much because I don't think it represents the stem numbers like you'll see often represented. Normally you'll see them right butting up against that division line. Oop, that was supposed to be a 4. It should be a 5, 6, etc., etc. And they'll be adjacent to that division between stem and leaves. Here too, you've got a key to show you how to interpret these data values for each of those. That's important for the stem and leaf plot, and anytime you would be asked to make one, make sure that you make a key so we can tell how to process what's going on. Okay, how is the area principle preserved by the stem and leaf plots above? Well, as long as the stem and leaf plot is well made, and it's easy, it is easy to make one that is not preserving the area principal. Again, part of the reason why it's a harder graph to make. Well, the area principal is preserved because, like I had pointed out before, with this bin that has a stem of 8 and then the leaves of 4, 6, and 8, you've got 3 data values falling into that bin. It is approximately 3 times the width of this guy right here, with the stem of 15 and the leaf of 1. And you're only changing the width of the bins. You're not also changing the height of them. So you can visually see, oh, okay, there are 3 times as many data values that fell into the bin with stem 8 than as opposed to stem 15. And there, the area principal is preserved. Okay, this is more the meat of the lesson, how we talk about shape, center, and spread for histograms in particular. And shape, center, and spread are really particularly useful for quantitative displays. We didn't talk about, and I got a lot of questions, which was awesome. You guys did a great job asking about how to describe the bar graphs and the pie charts that we saw. Well, we don't have as much that we can say about them. We don't have many general terms that we can run to use in describing what a distribution looks like when it's qualitative. But we do for quantitative distributions because, and it really hinges on this, it hinges upon the fact that the ordering, first, second, third, fourth, etc., of the bins for histograms is meaningful, while for bar charts it is not. If we look back to that example, okay, well this will work. I mean, if you were to make a bar graph out of brown, blue, and hazel eyes, the ordering of your bars, as we've said many times, doesn't matter. And it does for histograms. Okay, so the first thing we refer to is the mode, the modality of a histogram. You've got examples here of a unimodal distribution where that is in this first case, that is the highest bin. Okay, so the mode would be at whatever range of values this bin right here falls in. You've got a bimodal, bi meaning 2 in Latin. You've got a bimodal distribution in blue here, with modes occurring here and here. They are, for the calc people, they are basically like relative maxima. You've got a multimodal distribution third, which has modes, it looks like here, here, and here. We just go beyond bimodal. If you've got 3 or more modes, you just say multimodal for all of those descriptions. But what you might notice, especially in the multimodal distribution here, is that we're not talking about where are the peaks for these bins on the whole graph, but just relative to the bins around it. So this lowest bin is high relative to this bin to above it, and this bin below it, but obviously relative to the second blue one right here, it's low. So a mode is a relative concept, which makes it a little bit sticky, as you're going to see in this fourth example, as to how you might classify them. Excuse me. It's just a matter of feeling it out, and once you've described modes multiple times, you'll be pretty good at knowing whether or not you've got a bimodal, multimodal, unimodal distribution, etc., etc. This fourth one here, question mark, take a stab if you want. If you want to pause the video now, and well, I guess after I finish the instructions, if you want to pause the video, take a stab at trying to determine what sort of distribution you've got in terms of modality. Would you call it uni, bi, or multimodal? All right, so pause now if you want. Okay, so what I've seen in years past is that people want to call this a multimodal distribution because you have relative peaks here, 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 and here. When I think in actuality, well, not I think, I know that in actuality, generally you're going to call the modes actually to just be those 2 bins right there. Again, looking back to this last example, it really depends upon what's around it. You've got the shape of this distribution goes from falling here to rising, 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 okay? So you're looking at not only what is directly around it, like we see with these green arrows in the third distribution, but also what are the bins doing in general to determine whether or not that particular bin is a mode. So this is not multimodal. This is bimodal. All right, two prominent peaks. Okay, and there's modality. Modality actually can be used to describe bar charts. You can still talk about, if you were to think back to that first slide talking about eye color for students being hazel, blue, brown, etc., etc., which category people are falling into for their eye color is meaningful. You can still say, oh, okay, well, we've got a mode of hazel in this case, i.e. most people have hazel eye colors. Or I think on that first slide it was brown, a mode of brown eye color. All right, so also related to just describing the shape of a histogram, you've got uniformity and symmetry. I generated this data using Excel a couple of years ago. Just created random numbers, 1,000 random numbers between 0 and 1. So you've got decimal numbers that if you laid them all out, they would look like, let me go back to this slide, a much bigger version of the delivery time in minutes right here. That is to say, you've got 1,000 data values. Each could occupy its own cell, okay? But we're not going to do that. That's a pain in the butt. It's hard to process that much information, and your eyes see patterns and histograms so much more easily that it's laid out for you in a histogram here with, let's see, that would be a total of 10 bins. We've separated 0 to 1 tenths for the bin widths here. We've got 10 bins, and it is a uniform distribution. You don't have any prominent peaks. The data is kind of bumping up and down as you go across, but it's all the bins are relatively close to each other in terms of their counts or their frequencies on the vertical axis. So there's uniformity. Another thing that you want to look for when you're describing a histogram. Symmetry is just what you would expect it to be. If you cut a line down the center, is the data, ooh, not a very good line. When you cut a line down the center, is the data more or less, the shape of the data more or less the same on either side? Is it mirrored? In this case, yes, absolutely. So we would say that this is a symmetric distribution. You might see the word asymmetric come up, which would just be that it's not symmetric. I mean, just a fancy way of saying not symmetric distribution of the quantitative data. All right, skewedness. Skewedness is, I think, way more common than uniformity and symmetry. Skewedness refers to whether or not you're seeing a tail on the data. And thankfully, it's pretty easy to remember how you refer to the skewedness. Whichever side the tail is on, in this case you've got a tail over here, that is a right skewed distribution of quantitative data. You've got a left skewed distribution on the in the second example here. Anything else about this? What's wrong with the graphs above? Hopefully you noticed pretty quickly here that you've got gaps between the bins. That's a problem. Also a problem, you don't have good titles. And really, you don't have either axis named either. We don't know what type of quantitative information is being talked about here. Same with this. We also don't have the counts mentioned. That's a problem. I'm assuming that we have counts for these bins, but we don't know that, and there's no title. Okay, so those would need to be to make these good graphs, in addition to cleaning up the gaps between the bins. All right, outliers and gaps. Outliers are a big problem. Gaps, not so much. You've got, for this middle unit of line segment on a number line, let's see, what am I, middle unit of line segment on a number line, spaced on what was trying to be represented here. We've got, well, regardless, let's not focus on, I guess we can't focus on the context here because I'm not seeing what I was representing initially. You've got quantitative data cut into bins on the horizontal axis. You've got the frequency or the counts on the vertical. we've got that set up. You've got an outlier over here on the far right side, which is basically just a bin. It can be a couple of bins that are far removed from the main mass of the distribution. So you've got an outlier on the far right, you've got a gap right here on the right as well. Anytime that you have I'll need more space to write it than that. Anytime that you have an outlier, you will automatically have a gap. Just definitionally, outliers have spaces between them and the rest of the distribution of the data. But it's not necessarily possible that every time you have a gap, a separation between a bin and the rest of the data, that you automatically have an outlier, because you could have that gap that I just circled followed by more of the distribution looking something like this, okay? So you can have two big clusters of the data, which would mean you wouldn't necessarily have an outlier but still have a gap. So outliers always give you gaps, but gaps do not always give you outliers. Let's see. We've talked about, okay, let me recap real quick. We talked about outliers and gaps. We talked about skewedness. We talked about uniformity and symmetry. And we talked about modality, which is really the big one, along with symmetry, and describing the shape of a histogram of quantitative distributions. We have not yet talked about the center and spread. We said 4 descriptions of histograms. You want to talk about their shape, their center, their spread. We've hit shape. The center, for now, next chapter we're going to change this. For now, let me go back to a good histogram that I like. Yeah, this will work. Okay. For now, when you're talking about the center, you're basically just talking about where's the point on the horizontal axis, and it looks like it might be right about here. Where's the point in the horizontal axis that cuts on the left and the right sides into 2 basically equal areas? Because if the areas are equal, if all of this over here is equal in area to the red bins on the right, then you have the same number of counts to the left and the right of that cut mark, that division mark that you've just made. Okay, so I would say for this first distribution, let's see, that's separated by 5s, so it looks like about a 197.5 is your center for this first histogram, and for the second, it looks like it might be approximately here at 204 for your center, thereabouts. Okay, so just for now, just look at the center in terms of where can you cut the distribution in half. In terms of the spread, we can look at this guy to talk about the spread. To look at the spread, just tell me what the range of data values is between high and low. I would include 2 things when doing that. Tell me, so in this case, the spread is between, that's 248 Kelvin and 256, looks like it's right here, so that'd be 257 right here, 257.5. So the spread between 248 Kelvin and 275.5 Kelvin. And then, so that's one way to report the spread. Just what are the extremes of the data values that you see in a histogram? Say also what the range is. The range is just going to be the difference between those two. Get in the practice of naming both. So 275.5 minus 248 should give you, I believe, 27.5 K, 27.5 Kelvin. All right, so there's how you report the spread for now. We'll talk about that more next chapter. So the center is just where can you cut? So you've got 2 equal areas on the left and the right. The spread is the extremes, and then the difference of the extremes, which is the range. Okay, so we have a lot of terminology for describing distributions that we've seen. How would you describe the distribution based upon the terms we've seen today? So in terms of the shape, we've hit spread. The shape And you will need to do this in complete sentences. I would get in the practice of doing that in your homework, but for quizzes and tests, I need complete sentences because that's important on the AP exam. The shape, I would say, is multimodal. Okay, and I would report that you've got what looks like 3 modes. Maybe, I mean, you could argue a 4th here. That's fine, but at least 3 occurring at the bin 248 to 248.5. Then you've got another mode between 251.5 and 252.5 Kelvin. And then on the high end, you've got this bin at 257, excuse me, to 257.5. So you've got a multimodal distribution. You've got, you don't have skewedness. No skewedness. Okay. We don't have, let's see, modality, skewedness, gaps and outliers. We don't really have either of those. No, I mean, well, okay, let me back up. Some of you guys are going to want to say that we have gaps here, here, and here. Okay? There, too, a gap is a relative thing, just like a mode is. We don't have any significant number of bins without data values in them. I mean, yeah, we go 1 here, but it's not followed or preceded by another bin that doesn't have any data in it. Same way with this guy, we have another bin there, but it's not followed or preceded by an empty bin. So no gaps or outliers. We have approximately symmetric data. If you cut the center at about maybe here or here, just trying to do a quick eyeball on that, you more or less cut the data into an equally shaped left and right side. So you've got approximately symmetric data. And there we go. We've hit the shape. Let me see. So we said no skewedness. Let me see if there's anything that I missed just real quick. I don't want to miss anything. Skewedness, uniformity, symmetry. It certainly wasn't uniform. We talked about it being symmetric. We can say that it's not uniform. Yep, okay, so we'll say that it's not uniform, and that'll wrap it up. Okay. Or non-uniform. Okay, so we've knocked out the shape, the spread. We still need the center. Center, we actually kind of cut that just a little while ago when we were looking at the symmetry here. Center looks to be at about, I think if we're being really fair, we're probably going to say that it's right there. 252 is the bin below it. And these bins, when I looked earlier, go by 0.5. So the center would be at 252.5 Kelvin for this distribution. Okay, so there is shape, center, and spread. You will report those as complete sentences. I'm going to save time and not do that, just so that you're not taking notes all day. And there you go. There's your first. Let's talk our way through this next one, because I think if I just tell you what I'm seeing, it'll save time over writing it all out. So based upon the terms below, are again describing the distribution. We've got the cost of computer services rendered at a tech store. Well, let's start with the shape. The shape is certainly unimodal. You've got a bin that is the highest relatively and the highest compared to the rest of the graph, between 100 and 110. You do have skewedness. This is left skewed because the tail is on the left right here. You don't have a gap. You don't have an outlier. It's not uniform. It is, again, approximately symmetric, but the left skewedness, the left tail here, kind of throws that off just a tad. So there's the shape of the distribution. Then we'll go to the center. The center looks to be at about here, at about 100. And the spread, the data values fall between 40 and 140. And the range, the difference between them is then $100. Okay, so there is yet another characterization of a histogram. All right, So this is really I think, the most important thing you're going to see in the notes, because you're going to use this all year long. Yes, you'll describe shape, center, and spread of histograms, but being able to take data and throw it onto your calculator to make a display is really important. So you've got what's represented here. Let me give a context to this. I just made this table really quick. These are the monthly rises or falls, the monthly rising or falling of the Enron stock between 1997 and 1998 on a monthly basis. So if you're looking across the first row after the 97, you've got 12 data values from January through December. Same with the row below. And positive numbers mean the stock is climbing. Negative numbers mean the stock is falling for that month. So to do that, we're going to go to Wabbit. We are going to go to Wabbit. And I don't think you really need to use your graphing calculator to follow along. If you want to write things down as you go, that'd be awesome. I've already entered in the data values here. I'm going to open up initialized. And with these 24 data values, they want us to, well, they don't say this, but I want us to make a histogram here. To enter the 24 data values, you go Stat, then you hit Enter on Edit, and you've got all these lists, L1, L2, L3, L4, L5, L6, and then you can actually, well, it's not doing it for me right now. Oh, there you go. You can name additional lists if you want to help you keep track of what is what. Because if you don't clear these lists out when you do additional problems, you might get confused as to, oh, should I use L1, should I use L2, etc., etc. So you can, if you don't clean things out, you can just start naming your own lists, which is kind of nice. So I've entered these 24 data values in. You just enter it in using the keys, and then when you hit Enter, it automatically takes you down to the next cell or the next row, so you can enter in a new data value. So I did that 24 times. And nice thing about this, it's telling us the number in parentheses is the number of data values that, or where that falls in the list of data values. So this 0.78 is the 13th data value. Going down the line, we've got negative 0.5 is the 24th and last data value. So it's a nice check. If we know that there are 24 data values in the table, seeing that 24 is in parentheses for that last data value of negative 0.5 tells us that we could have, but we maybe and probably did not skip any data values. So I left that one blank because we don't have a 25th data value. All right, so from there, we're going to go second y equals to hit the stat plot. And, oh, thankfully, this looks like it's set to the defaults right now. So none of the plots are on, none of the stats plots that we would want to have are on at the moment. That's good. We're going to hit Enter on this first one. We're going to turn the first plot to on rather than off. And you've got 6 different displays to choose from here. The first one is really common towards the end of the first semester. It's a scatter plot, and we'll see that later. Second one is a I don't remember what that one is used for. I don't know why I'm blanking on that. Third one is a histogram. Then you've got a couple of box and whisker plots with 2 different options there, and then a cumulative frequency plot, which we'll rarely use. Well, we want the histogram for now, because that's what we're playing with today. The X list is set to L1. That's good. That's where we entered the data already into L1. And the X list refers to which axis the X list, or you could say the Y list, will get the quantitative information. Well, histograms display the quantitative data on the horizontal axis and then the counts on the vertical. The count, you want to set frequency to 1 or just leave it at 1, because that means that for each data value in L1, it will be represented as a single data value, as one data value, as opposed to 2, or I hit, let's see, let's go there, and there's my alpha key. As opposed to 2, then each data value in L1 would be represented twice, which we don't want. So just leave that at 1. And then to graph this, the easiest way is to hit the zoom button, and this is really nice. You're going to go zoom and then 9, or then zoom and scroll down and hit zoom stat, and you've got a histogram. as you can notice, there are 6 bins in this histogram, which is cool. We've hit the middle, or the number of bins that we would want to shoot for most of the time. 6 to 8 gives us a nice display. But as it's set up right now, as you can tell, obviously there's no title. You've got to come up with that on your own. When you take this graph that you're seeing on the 84 and try and transcribe it over to paper, there's no description of what the axes stand for, of course, because we just entered data. We didn't tell it what the variable was. And we don't know how tall these bins are currently. So to get that, hit the trace button, and it will, you can hit left and right, and it'll go from bin to bin, and it'll let you know in this number right here is the number of data values that fall within that bin. So on the far right, we've got 1 data value in that bin. We've got 3 to its left, 9, 9. So there's sort of your mode, 1 and 1. Okay. Min and max tell you what is the lower division for that bin and what's the upper. So min is this bin cuts off at negative 4.5 here and negative 3.06 repeating, which is basically negative 3 and a 16th. All right, so the next bin cuts off on the low end at negative 3 and a 16th up to negative 1 and 5/8, I believe, right here. So what you're going to notice is that the TI-84 will do an awesome job of cutting up the bins so that you've got a pretty histogram, but the bin width sometimes is a real pain in the butt. So to change that, let's say we don't want bins that go from negative 3 and a 16th to negative 1 and 5/8. It's just kind of clunky. You're going to go to Window and then down to, let's find it, down a little bit further. Wait, really? X-min, X-max. Oh, there it is. X scale right here. And it's set to this really nasty number. Instead of setting it to 1.4 whatever, let's just change it to 1. Now the bin width will be 1. And let's go back to zoom, oh, nope, not zoom stat. I'm sorry, because it's going to reset the X scale. It's actually probably good that I did that. 1, and then we'll go back to graph this time, not zoom stat. And there you go. You've got more bins, but now the bin width is much easier to transcribe on paper. So we're going to hit trace. We see that there's 1 data value falling in that bin between negative 4.5 and negative 3.5, 0 in the next, 1 from negative 2.5 to negative 1.5, etc., 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 etc. So we've done a little bit more cutting up of the histogram, but it's going to be easy to write down.